All right. So typically when I start off a class, we'll come into one of the modules and we'll start going through the PowerPoint. There are these handouts. Now, what I did this year, because I had a few people say last year they wish they didn't have to print out so much in different classes, not necessarily the ENS ones. So chapter 1 PowerPoint is here, and this has basically, it's basically like a high level review of what's in the textbook. So if you have the PowerPoint, let me open the PowerPoint. If we're going through the PowerPoint, right? What is a circuit? What are the units? Like charge, right? This slide on charge, there's obviously a lot more detail in the textbook on charge, right? Besides these two slides. But this is sort of an overview. So then I can get into doing some problem solving. If you're looking for the problems I'm going to do, I've got them in two different file formats. The one with the HO is just handout. It's all the problems are on a single page, if I can fit them on a single page. So if you look at this file, all the problems that I'm going to cover for chapter 1 are on this page. If you want actual room to write, the worksheet file here has all the problems spaced out. So this is what I'll actually use when I'm going through the problems, right? It's got spacing to write the solutions. So you can see this takes up what, 4 pages. But some people didn't like printing out a bunch of the a lot of different pages, so you can just print out one, or you can even just download this and reference it. These are all the practice problems from your book, except I think this one, because there wasn't a good practice problem. I don't remember why I chose the example. But in your textbook has example problems and it has practice problems. And the example problems are worked out for you. The practice problems are not. The practice problems just have solutions. So I thought, you know what, those are problems, those are good problems to choose and go through to show the concepts. And let me show you, if I can find one. Oh, here's a practice problem, yeah. Switch over to the document camera here, which is not, needs to be reset. There it is. So here's an example problem. I'm going to make this bigger. Yeah, here's an example problem. It tells you, it shows you how to do it. I mean, this is a very brief solution. And then the practice problem. The practice problem gives you an answer. Occasionally, the practice problems are, I'll try to remember to point them out. The practice problem I show may not have the same numbers just because there was an error somewhere. I have found errors in some of the practice problems, but that's what I'm doing when I'm covering the practice problems. Let's see, close that, and then videos. So I'll post the videos to related to the module here. And typically they're posted by the end of the day, sometimes the next day. I have to download them from the Zoom account and upload them to YouTube because I think Zoom has limited storage. Well, it's supposed to. And then I'll typically put the homework in here. If there's a quiz or the quiz for the module, I'll put in the bottom. Well, you know what? Let me ask you guys. So those of you who had the classes last semester, would you prefer, so last semester I put the quizzes in the module or the tests in the module. Would you prefer a separate folder for quizzes and tests? Or does it not matter? Just organization wise, does it make a difference to you?
Not really.
Okay, because some of my first year classes, I had them in separate folders just because there were so many folders. But if you're okay now, oh, the other thing I want to show you here is in Blackboard, which, Oh, I guess I got to exit to show you. Up in the corner in a minute. Oh, wow. All right. Up in the corner here, you should see your name. And if you don't know about this feature, it's really going to be handy for you. If you click that, there's a drop-down menu. And mine is just a disaster because I've got courses from other semesters, and there's a little calendar icon. If you click that calendar icon, it takes you to your calendar. And again, I don't know how to delete these on mine because they just sit there. I've checked off the ones for this spring semester, right? So I've got 5 classes checked off. And in the calendar, I can see due dates for things, right? So let me hover over, what is this? This is for my PHS 101 class. They've got an interaction, scientific method discussion due on January 27th, right? So you can see all your due dates for your classes as long as the instructor is using the assignment due date. Now, let's see, which one is circuits? Is it black? Okay, well, that's mechanics. Oh, what is this one? Oh, here's Intro to McGraw-Hill. Let me go to the next month. I didn't put too many that far ahead. What is this class? I haven't figured out the colors yet. It's dynamics, it's mechanics. Where's circuits? Cancel. Physical science. Why am I not seeing circuits here? All right, I got to look at the color. Circuits is this blue. Oh, it is. Okay, it is here. All right. Yeah, so chapter 1 homework. All right, engineering circuits. So even with the McGraw-Hill Connect, if I put a due date in, it's going to show up. And when I link it to Blackboard, it'll show up. So those McGraw-Hill assignments will show up here as when they're due. So this calendar is kind of nice. You can sort of look at all your Blackboard assignments in one spot, right? And you can color code them if you can remember what color is which. For some reason, I can't. All right. And again, I don't use it enough to really, oops, I gotta go back. But that's another place to find all your assignments. All right, any other questions? Let me jump over to the PowerPoint. We don't have that much time, but we have enough time to actually go through some of this stuff. See, it's 10:30, the class ends 10:45, I believe. Yeah, so the first chapter is actually fairly basic. I think you probably covered some of the stuff you've definitely covered in physics 2. Other stuff might be new to you. And we're going to start off with things like voltage and current and discuss some rudimentary circuits. Chapter 1 also has like a whole section on problem solving. The thing about circuits is there doesn't tend to be one right way to always solve a circuit. There tend to be easier ways to solve circuits and harder ways. So choosing the right methodology is sort of, it helps if you've done a lot of homework problems. But anyway, what's a circuit, right? It's basically just a bunch of electrical elements that are interconnected, right? And you can see here, they've got a microphone and an antenna, and there's a whole bunch of symbols in here, right? And we're going to look at things like resistors and capacitors. I can't remember the transistors. There's part in your book, if you're interested in transistors, you can look at some of the information in your textbook. We're not going to go into detail in transistors. And here's an inductor over here. But this is a basic circuit for for looks like a basic radio, right? 9-volt power, a microphone, an antenna, and all the circuits in between. So this would be your typical transistor radio, right? And so that's a circuit. Now, when we talk about some of these resistors and capacitors, we're going to use units, and we're going to use SI units. You guys should all know this stuff, but you're going to see sometimes you're going to see some small measurements. Like you might see things like femtofarads for capacitors, or microamp or milliamps, right? There's a lot of problems in the textbook that use milliamps, milliohms. I actually worked in an industry where we were doing capacitors for computer memory, and those are on the order of femtofarads and picoamps, and femtoamps. Those are the type of measurements you're looking at. So it is possible to measure down to this level. And they do that all the time in the electronics industry when you're looking at things like, computer memory and transistors in your computer. And computer industry is a good example of a lot of disciplines working together to create something, right? I worked with when I worked in the semiconductor industry, I was working on the process development end of making capacitors, right? Very small capacitor structures for DRAM that you use in your computer, and they're made on a wafer, right? And they're made by depositing thin layers of ceramics or metals, and that's got chemical engineering, it's got material science, it's got electrical engineering. We had physicists working there. What else? We had not too many mechanical engineers, but yeah, a lot of chemical engineers for the process end, a lot of electrical engineers for the circuit designs, and then material scientists and physicists. Oh, and some chemists too. So you're working with a lot of interdisciplinary groups to develop these things, and it helps to be able to communicate with the people outside your discipline. So let's see, charge. All right. When we talk about electricity, we're looking at charge, right? That's the basic unit, and it's measured in coulombs. And what does that do? It counts the number of electrons, right? Now, in the old days, people used to think it was positive charge that moved. So you're going to see a lot of notation in circuits that comes from this idea that it's the positive charge that's moving, right? Not the negative charge. And obviously now we know it's a negative charge. And so it can get a little confusing because you're thinking, well, electrons are moving, but we're saying the current's coming from the positive electrode. Well, that's the way the convention is. You just kind of got to get used to it. And it gives you the charge of a single electron. So that first homework problem you saw, right? It gives you, I can't even remember what it was now, but it asked you for it asked you some question that was based off of this, right? One electron is 1.602 times 10 to the minus 19th coulombs. And again, these numbers are going to be in your textbook. This is why I like teaching sort of, if you were in class, I would give you a formula sheet, right? But open book is great because now I don't have to worry about making up a formula sheet. I don't expect you guys to sort of memorize all this stuff. If you work in an industry, you're going to start remembering a lot of this stuff just offhand, right? Like, for example, I worked with the ideal gas constant so long that I would just remember it, right? But I would remember it in different contexts. Like when I worked at Micron, I was always using it in very low pressure units. So very like torr, and I don't even remember what that one was. The last time I used it was in units of meters cubed Pascal mole Kelvin, right? 8.3145. So I remember that one. So depending on how you're using these things, I don't expect you to memorize them and remember them all the time. You look them up, and when you start using them enough, you're going to remember them. Yes, charge. Okay, so charge, right? I already talked about this. picocoulombs, nanocoulombs, microcoulombs, right? Those are the type of units you'd see if you're doing some kind of measurement in the lab. And it's always some multiple of electron charge. So just like well, what other classes you learn this in physics, right? Charge is it's not created or destroyed, it's only moved, right? So we talk about things moving, charges moving through a wire, right? Just like we talk about water flowing through a pipe, right? If you put in 10 gallons per minute on one end of the pipe and you're getting 5 gallons per minute out, you've got a massive leak somewhere, right? Because you're not destroying water and you're not creating water. The same thing with charge, right? The charge in equals the charge out of that wire. And if you don't have that conservation of charge, you're losing it somewhere. And that's actually what we used to use for a capacitor to determine how good our capacitors were, right? You would charge up your capacitor and you look and see, okay, what's the charge after a certain amount of time? And capacitors have what's called a leakage rate, right? So charge, they lose charge over time. You know, some capacitors are better than others. Your computer memory, DRAM, needs to be refreshed because the capacitors lose charge. And that charge just sort of dissipates. It leaves the storage, the storage electrodes, because you get leakage. These devices aren't perfect. You get leakage outside, and you lose charge. So you have to refresh it. Your USB drives, right? Your read-write, the SRAMs or the flash drives, right? The flash memory holds the charge. And in fact, there's other memories that actually adjust. There's a physical state change in the device, so you don't actually have to store charge at all. So yeah, movement of charge is a current, and this is where it gets confusing, right? Moving charges were always thought to be positive. This is in the old days, right? When electricity was like new and exciting and no one knew anything. So we always write this convention. If you see a battery, right, you write that the charge or the current, right? The current is flowing from positive to negative. Now, notice here, if you're applying a current to this object, right, the electrons are moving. The electrons are moving in the opposite direction. We're saying the current is going positive to negative. That means that the negative charges are moving in the opposite direction, right? Any questions so far? Current. This is, you're going to be taking some derivatives in your first homework, and you'll probably be doing some integrals too, because current, right, is basically just charge per unit time, right? So if you're given some function for current, you can integrate that and get charge. Or if you're given some function for charge, right, you can take the derivative with respect to time and get the current. So I think there's some basic problems in your first chapter homework that just deals with, you know, here's the charge per unit time, or here's the charge as a function of time, find the current, or here's the current, find the charge pass through in this amount of time, right? So if you know the current and you know how long the current flows, you know how much charge you transferred, right? If you know how much charge per unit time, you know the current. And the unit for current is amps, and that's a coulomb per second. Oh, so here's one of the examples. You know what? I think I'm just going to pick. Oh, this is an example from the text, not from the. So this is right from your textbook, right? Page 8. What charge is represented by 4,600 electrons? So now you know, okay, the charge of a single electron, notice it's a negative, right? Electrons are negatively charged. It's 1.602 times 10 to the minus 19 coulombs. You just multiply that by the 4,600 electrons and you get that charge. Here's another example. Oh yeah, so this is the charge entering a terminal is given by this equation, right? Q is 5t sine 4 pi t. This is millicoulombs. Find the current at time is 0.5 seconds. So remember here, current is the derivative of charge per, it's charge per unit time, right? The change in, so we've been given a function that tells you how the charge enters a terminal as a function of time, right? So, I mean, if this was just a constant, we would, and we were told the time, it would be easy, but here we're given an equation. So we've got to take the derivative of it, and you just, you put it into the brackets there, you take the derivative and you wind up with an equation that tells you that current is 5 sine 4 pi t, right? You're just using the product rule, 20 pi t cosine 4 pi t. So now you have an equation for current based on knowing the charge entering the terminal. And then you just evaluate that at 0.5 seconds. What did I do here? Oh, I plugged the numbers in. This just simplifies everything, right? And you wind up with 31.42 milliamps. Watch your units. This is a millicoulomb. So when you wind up getting the current per time, it's going to be in milliamps. So yeah, you could obviously multiply this by 1,000 to get amps. But that's the biggest thing, I think, in the chapter 1 stuff is just watch your units. Because the derivatives and the integrals, you guys are probably experts at by now. Yeah, so I'll pick up here next time. Go ahead and print out the practice problems from the module 1. Again, you can print out the just a handout or the worksheet. You don't have to print both of these. Print out whichever one you want, whichever one you're more comfortable with. Again, I put the handout in there because some people just wanted to have the sheet of paper, and then they'll write it down in their notes and reference that problem. Any questions before we stop?